Hello there. I'm glad to share this quiet with you. Let your shoulders ease down as your breath finds an easy rhythm and the room grows soft around the edges. Nothing urgent tonight. Just a calm voice, a patient pace, and a small question to hold gently in your hands. We're going to sit with the idea of time itself, where it comes from, and whether it ever truly began. Some people ask what came before the universe, but that word can feel like a compass pointing past the edge of the map. Maybe time isn't a road that stretches forever in both directions. Maybe it's something that appears when the conditions are right, the way ripples appear only when water is there to carry them. If this gentle journey helps you unwind or stirs your curiosity, a quiet like and a soft subscribe help others find their way here too. For now, breathe in, breathe out, and let your thoughts settle like dust in a sunbeam. Close your eyes. We'll begin together. Imagine starting from stillness and easing into motion, the way a boat slips from the dock and the water accepts it without a sound. At first, nothing seems unusual. The room is the room. The sidewalk is the sidewalk. The night sky holds its steady scatter of stars. But as speed grows and keeps growing far beyond anything a car or a jet can manage, the familiar begins to tilt. Questions you've heard before float up. What changes if you move close to the speed of light? What does the world look like? How do space and time behave when speed stops feeling ordinary? The answers sit just beyond everyday intuition, but they're not cruel or complicated. They're simply different, and they reveal themselves one gentle step at a time. There's a rule at the center of all this. Light is the same speed for everyone, in every direction, no matter how you move. Because that speed refuses to budge, the things that can change space and time do the bending instead. Another truth walks beside it. Anything with mass can't reach light's speed. The energy you'd need swells and surges without bound as you push closer to that limit, climbing so sharply that the finish line recedes like a horizon. Only massless travelers, photons, get to live at that pace, and for them the passage of time is not a passage at all. Still, matter can come close. We've watched tiny particles in accelerators and cosmic rays from space fly at 99% of light speed and beyond, brushing the edge as if skimming a lake with a fingertip. If your body could somehow ride such a current, the first changes would arrive through your eyes. Color would begin to drift. Light carries itself in waves, and color is simply the size of those waves. Long waves, paint reds. Short waves, tint violets. Beyond what we can see lie the warmer stretches of infrared and the sharper glint of ultraviolet. When you move quickly into light, the waves meeting you are squeezed, their crests pressed closer together. Waves behind you are stretched, their crests pulled apart. This is the relativistic Doppler effect, kin to the way a siren's pitch climbs as it approaches and falls as it leaves. Except now, the pitch is color and the instrument is the universe. At modest speeds, the change is subtle, like a whisper in a crowded room. Push faster, and the whisper becomes a clear voice. Light that used to hide below red may edge into vision. Heat that normally glows in infrared begins to show its hand, and the pale tongues of ultraviolet drop toward colors you can actually see. Surfaces take on strange moods. A cool blue sign you know from your neighborhood may harden toward white when it's straight ahead of you, while the same sign, if you glance back, slides toward a deeper red. It's not magic. It's the way motion remixes the wavelengths you receive, shifting part of the invisible into the visible and pushing part of the visible out of reach. The faster you go, the wider your personal window onto the spectrum becomes, though what you see depends on where you look relative to your motion. Brightness changes too, and it changes with a kind of focus. Imagine moving into a gentle snowstorm. When you're standing still, flakes drift past from all directions with no particular emphasis. Start running, and the flakes seem to meet you from the front more than the sides or back. Light is made of photons, little quanta, tiny parcels of energy, and when you head into their stream at high speed, more of those parcels meet your eyes per tick of your own clock. The view ahead brightens, sharpened by a forward squeeze of the light called relativistic beaming. Turn your head and look behind, and it's as if someone has dimmed the world. Fewer photons reach you from the rear in the same slice of your time, and the ones that do are gentler, stretched toward longer wavelengths. Pilots sometimes call this overall pattern the searchlight effect, a tunnel of brilliance where you're going, a deepening dusk behind. After color and brightness, another shift arrives, less obvious but even more profound. Your sense of distance begins to loosen. You still feel your own pace as steady. Your steps, if you could take them, are still steps. Your heartbeat holds its rhythm, yet the space ahead seems to give way more quickly than it used to, as if the road has been quietly folded and you are crossing each fold in fewer moments than before. What you're noticing is the partnership between time dilation and length contraction. The names sound technical, but the feeling is simple. Your time, measured by your own clock, runs slow compared with the time a person at rest would read, and the distance in the direction you're moving shrinks compared with what that person would measure put together. The trip that once felt long now feels gentler and shorter from where you sit. This is not a guess. We've tested the slowing of time with clocks you can hold in your hand, identical atomic clocks, careful, patient instruments ticked together on a table. Fly one quickly and bring it back, and when you compare, the traveling clock lags. Satellites circling Earth feel it too. Their clocks drift a little from the ones on the ground and need corrections so that maps, phones, and timing systems keep their promises. The difference is small over a day, measured in slivers of a second, but small things add up, and the principle is the same at any speed. The faster the motion, the stronger the slowing, with the extreme case being a photon for whom the tick never moves at all. Once you accept that your moments are stretching compared with someone else's, a curious tenderness enters travel. If you rode in a craft that could nestle close to light speed and you journeyed for a single year by your own clock, the world you left could count far more than a single year before your return signal ever reached it. Numbers depend on the exact speed, but the idea is steady. From your seat, life feels normal. You read, you rest, you mark a birthday, and yet back home, anniversaries stack up like pages. The old thought experiment says, imagine a destination 40 light years away. From your perspective, if you truly rode the very edge, arrival would feel immediate, because from your frame, the distance has collapsed to almost nothing. Back on Earth, though, 40 years would pass before your hello reached their sky. That contrast is not a trick of language. It is how the world keeps light speed constant, while granting different travelers different slices of time and space. There's one more bend your eyes would learn to recognize, and it may be the strangest to describe because it is a shape made from seeing. As your speed climbs, the world seems to draw itself into a forward cone. Directions you used to experience as sideways, even a little behind, are pulled toward your path ahead. A wide sky narrows. A distant landscape seems to gather and lean toward the center of your motion. This is aberration of light, and it's born from the simple fact that light takes time to reach you and that you move during that time. Think of raindrops falling straight down. If you stand still, they prickle evenly on a hat brim. Start walking, and the drops land more on the front. Start running fast, and it feels as though the rain slants into your face, even if it keeps falling straight. Replace raindrops with photons, and your swift motion changes the apparent angle from which they arrive. The geometry squeezes the whole panorama forward. Stars you once saw off your shoulder drift toward the center of your view. The rear world recedes, dim, reddened, and trimmed by the same squeeze in reverse. Fold these effects together, and a traveler near light speed moves through a world that is both familiar and remade. Colors shift with direction. The forward scene brightens and tightens. Distances shorten along the way you go. Your own time feels unwavering, yet compared with someone resting far away, your minutes are longer, your hours are fuller, your days are more generous with their capacity to hold you. None of this breaks the everyday truth that you can't reach the speed of light if you have mass. The energy bill rises too steeply. But too steep is not the same as nothing happens. There is a wide country of almost, and in that country lie the changes you can feel and, if you're careful, even measure. It's also worth remembering that everything we see is a moment that has already happened. Light needs a little while to cross any distance, even the arm's length between a screen and your eyes. The delay is tiny, smaller than breath, but it's real. Look at the moon, and you're seeing it roughly a second ago. Look at a star, and you're looking back years. Speed only deepens this sense of looking into the past. When you move very fast, the time that light needs to reach you braids with the time your own motion takes, and the braid changes the angles and colors that arrive. Some of these shifts were captured in a playful demonstration built years ago by curious minds. Instead of making you run faster, it imagines what would happen if light itself were slowed toward walking speed. Pick up glowing tokens. The world begins to change. Colors rearrange. The forward view sharpens. The hallway ahead seems to grow short. The trick works because the key ratios are what matter. In the real world, you cannot slow light in open air, and you cannot walk anywhere near its true pace. Yet the relationships, how color responds, how brightness swings forward, how distance and time trade their favors are the same. Think of it as a mirror held up to the rules, one that lets you see them with your feet on the ground. The longer you sit with these ideas, the gentler they feel. They don't ask you to juggle equations. They ask you to trust a few steady truths. Light keeps its pace. Anything with mass pays dearly to chase it and never quite arrives. Speed shifts color, gathering the sky toward your path, and time so rigid in ordinary days loosens when you move fast or stand near heavy things. Distance from your seat shortens along the direction you travel. Put a person in that weave, and you get a story that's both wondrous and plain. A traveler who feels normal inside a small cabin, a home world counting seasons more quickly outside, and a reunion that is warm and late by someone's clock. Even a photon hints at how deep this goes. If you could ride with it, an impossible thought, but a kind one start and finish would touch, and the idea of during would fall away. Step into that imagined world, and a subtle mismatch begins to show between where things seem to be and where they are. Walls slip a breath to the side, doorways arrive a beat early, and your hand closes on a spot an object has already left. It feels like lag. Only the delay isn't in a wire, it lives in the light itself. As the effective pace of light drops in the simulation, the picture you see belongs a little further in the past. You stand here, but the scene reaching your eyes left there an instant ago, and that instant lengthens as light slows. Steering becomes a quiet trust. Turn a touch sooner than habit. Aim for where things are going rather than where they were, and you meet the future position instead of the past image that keeps arriving late. That gentle dislocation also widens the world. As speed climbs, a greater share of your surroundings crowds into your forward view. This isn't the universe expanding. It's the angles of incoming light shifting because you're moving while those photons are still en route. Imagine a lighthouse beam sweeping across a shoreline at night. If you stand still, you catch the beam when it points at you. Start walking toward the lighthouse, and you'll meet that beam a fraction sooner at a slightly different angle because you've closed part of the distance while the light was on its way. At very high speeds, that tiny geometry becomes a full experience. Directions that once felt sideways drift toward the front. The scene ahead tightens, brightens, and seems to gather itself into a cone. The sky doesn't actually fold. Your motion reweaves how the past light of that sky arrives. A quiet truth sits under this. Every sight is already a memory, even across the small gap between a screen and your eyes. Light needs a moment. The delay is tiny, barely a thread, but it's real. Stretch the distances, and the delay grows. Look at the moon, and you're seeing it as it was about a second ago. Glance at the planets and stars, and you're looking back minutes, years, sometimes centuries. When you move quickly, your motion and those delays add together in an intricate braid. The braid explains the feeling that you can see more at once, because light from a wider slice of the world is redirected into your forward gaze, and it explains the odd necessity of turning early, because you are forever chasing the position an object had when the photons left it. The game that slows light is a playful doorway into these ideas. In real life, light racing through empty space does not dawdle the way a tune can slow down on a turntable. But if you imagine it could, the same relationships appear, only made large enough to feel with your feet. Colors slide because wavelengths shift. The front view brightens because more photons reach you per tick of your own time. Distances seem shorter because your personal clock runs slow compared with the rest, and the path ahead is measured by your clock. None of this claims to capture every consequence. If the world truly had a slower light, even ordinary days would tangle. The Earth spins and orbits. Electronics rely on signals timed with exquisite care. The dance of atoms, GPS, radio, and power grids all lean on the constancy of that speed. The thought experiment sidesteps those complications and lets you taste the visual, bodily side of relativity, how the world looks and feels when motion becomes a large fraction of light's pace. If a ship could skim that boundary in the real cosmos, the view out the window would carry the same signposts, only brighter. The field ahead would narrow and intensify. Colors from objects you face would shift toward the blue, while those behind redden and dim. More of the spectrum would slide into range, making invisible things warmth that usually lives in infrared, glints that usually sit in ultraviolet drift toward colors you can see. And the trip itself would inherit that double nature, of distance and time. Inside the cabin, your rhythms would feel normal. Meals, sleep, the slow flip of pages. Outside, measured by clocks that stayed home, the seasons would pass more quickly. Travel far, turn back, and return, and the planet welcoming you would carry extra years compared with the ones you counted. This is not a trick of language or a glitch in the math. It's the universe honoring light's fixed speed by letting different travelers carve different paths through time. The same story appears on smaller stages, where numbers are gentle enough to measure with patient instruments. Two clocks that agree while sitting side by side will slip out of step if one spends hours flying fast and the other rests. That comparison has been done with atomic clocks that tick with steady certainty. The difference, after the flight, is small, but exactly what the theory promises. Satellites circling high above Earth feel it too. Their orbits sit farther from our planet's pull and carry a different speed, so their time does not match ours perfectly. Engineers fold both effects into their design motion and gravity so that navigation and timing remain trustworthy on the ground. Gravity's part deserves a quiet moment. Time does not only care about speed, it cares about where you sit in a gravitational field. Closer to a massive body, time runs a little slower. Farther away, a little faster. This isn't a poetic metaphor, but a measured fact. In a landmark test, a beam of gamma rays was sent from the top of a tall tower to the bottom and examined for a change in frequency. The light falling down, moving into a region of stronger gravity, arrived with its crests packed a little closer together, its frequency slightly higher, matching the prediction that clocks and the processes that act like clocks slow nearer to mass. Physical intuition helps. If you imagine time as a flexible fabric, then mass makes a gentle well in that fabric, and clocks lower in the well tick more slowly than clocks up on the edge. That flexibility touches even the smallest ideas we keep about a day. Mercury turns slowly, completing one rotation in about 58 days, 15 hours, and 30 minutes by Earth's measure. That number describes how long the planet takes to spin once relative to the distant stars. Being so close to the Sun, Mercury lives near a deeper gravitational well than we do, and the curve of its path and the pull it feels both shape the way time passes there. If you stood on Mercury with a careful clock and a friend stood on Earth with the same model, the two of you would not agree perfectly after a while. Motion contributes. Gravity contributes. The effects are tiny over a single afternoon, but become meaningful when you use them to guide spacecraft or synchronize signals. They do not grant a secret path to long life by moving house to Mercury. They tell us that 1 second is not the same everywhere when gravity and speed differ. It helps to step back and hold a simple picture. You and everything around you are always moving through space-time. When you move more through space, you are, in a sense, moving a little less through time compared with someone resting in a weaker gravitational field. That trade keeps the speed of light steady for everyone. It keeps the equations elegant, yes, but more than that, it keeps our experience consistent. A signal leaving a satellite, a heartbeat in a chest, a photon leaving a star, each follows rules that match on contact, so that when they meet, the world doesn't disagree about what happened. The price is that our everyday intuitions, built in rooms and parks and on slow streets, don't automatically prepare us for what happens when speeds are high or gravity is strong. Once you see that, small details in daily life take on a new softness. The fact that your phone can tell you where you are depends on adjusting satellite clocks by tiny amounts to account for motion and height above Earth. The fact that astronomers can weigh a galaxy or test a theory depends on catching shifts in frequency as light climbs out of or falls into a gravitational well. The fact that two clocks flown apart and brought back disagree by a sliver confirms that time itself is not a background grid but a participant, responsive and alive to context. Even without ships and towers, you can feel the shape of the idea by watching how sight behaves at speed. When you imagine moving quickly through a hallway, your mind draws the brightness gathering at the center, the colors ahead hardening toward blue, the sense that you must aim a little early to thread a doorway that is, in truth, already a few moments in your past. When you imagine looking back, your mind knows the scene would dim and redden and seem farther away than it should. These are not random quirks, but the natural signatures of a world in which light obeys a single pace and everything else flexes to keep harmony with it. There's a quiet beauty in that harmony. A photon leaves a star and spends no time at all by its own measure to reach a leaf, a camera, an eye. A person rides a plane or orbits a planet and finds their clock just slightly out of step with its twin on the ground. A tiny beam in a tower picks up a whisper of extra frequency as it drops. A planet near its star rotates slowly, carries a deep well of gravity nearby, and would host clocks that tick at a tempo we can predict before we ever go. Each of these is a small window looking in on the same landscape. So when the game makes you miss an orb you were sure you would catch, think of it as your first conversation with that landscape. You saw the object where it was, not where it would be when your hand arrived. You felt your field of view swell as the math of aberration nudged more of the world into your forward sight. You sensed time and distance trading favors, the walk still a walk by your own reckoning, yet the hallway somehow shorter. Carry that sensation outward, and a pathway appears for understanding why a swift trip could feel brief to the traveler and long to the people at home, why Mercury's neighborhood near the sun tugs a clock's pace, why signals and maps need tiny corrections to stay faithful. None of this breaks the spell of a quiet night or asks you to wrestle with heavy equations. It simply invites you to hold a few steady ideas and watch how gently they explain 1,000 small wonders. Light keeps its speed. Motion and gravity answer by reshaping time and sight. The world you see is always a little earlier than the world you're in. Near light's boundary, colors and brightness and angles change in ways that match those truths. And back here, at ordinary speeds, the same rules whisper in softer tones, small offsets in clocks, faint shifts in frequency, careful adjustments that make our tools and journeys work. If a traveler ever slips close to that limit and writes home, the note will carry familiar marks, a view narrowed and brightened, colors leaning blue ahead and red behind, a journey that felt brief, while the home they left counted long seasons. On a smaller scale, two quiet clocks say the same thing, a patient one on a hilltop and another at sea level. Their tiny disagreement, a pocket-sized echo of the larger story. From a playful simulation to a planet's turn to a satellite's arc, the lesson stays gentle. Space and time aren't rigid walls but responsive companions, making room for light to keep its promise while letting us move through a universe that remains steady, measurable, and at night, very calm. So when someone hears that Earth's gravity slows time, the mind's quick double take softens. The ground feels solid, the days keep their rhythm, the kitchen clock ticks along, How could standing on a planet matter? Perspective does the explaining. Your own time always feels normal thoughts in order, 1 second following the next. The slowing only shows up when clocks are compared. One living deeper in a gravitational well. One resting higher where the pull is gentler. Set them side by side, let them run, then bring them together again, and a tiny offset appears. The clock that lived closer to mass lags by a breath, as if gravity had asked time to take smaller steps. The Traveler's Letter and the Hilltop Clock are two verses of the same song. That's why the question, how much faster would time be going for me if I weren't on Earth, needs a careful reply. From where you stand, it isn't faster or slower. It's simply yours. What changes is how an outside observer or a second clock carried to a different place would measure your passage. General relativity gives a compact way to compare those two clocks. You can imagine a reference clock very far from any mass, coasting in a region where gravity is essentially absent, and another clock resting at some distance from a massive body. The comparison depends on a few steady characters: the mass that's pulling, the distance from that mass's center, the universal gravitational constant that ties mass and space together, and the speed of light, which anchors everything. If the symbols feel chilly, translate them into a picture: bigger mass, closer distance, deeper well, slower ticking. Carry that picture down to Earth and try a simple test case. Suppose a perfectly placed, far from everything reference clock counts 60 seconds. How much time slides by on a clock here on the ground? The kind you could touch. Plug in Earth's mass, the radius to its center, the unchanging speed of light, and you get a figure so close to 60 that you have to squint to see the difference. About 59.999996 seconds. It's a whisper of a change. Put it another way, roughly 6 billion seconds would need to pass on the reference clock before Earth's clock fell behind by 4 seconds. 6 billion seconds is about 190 years. Over a long human life, that comes out to around 2 seconds. A blink, yes, but a measured blink all the same. Earth doesn't live alone in space. Of course, the sun's gravity reaches us, and though we are far from the surface of that star, its mass is so large that its contribution matters. Keep the same comparison 60 seconds out at the quiet edge, clocks down here on Earth, and include the sun's pull along with Earth's. The result steps a little farther from 60, about 59.99994 seconds. That translates to roughly a 1-second disagreement every 3 years, which, over many decades, adds to about 24 seconds. Suddenly, the effect feels less ghostly. It's still small, but it's not nothing. Your GPS and communication networks quietly account for corrections like these. Engineers bake them into the design, so your phone and maps keep their promises. If proximity to the sun slows time, Mercury ought to offer a stronger example. That small world orbits much closer to the source of light and heat that rules our system, sitting deeper in the sun's gravitational well. Keep the same thought experiment. A faraway reference clock counts 60 seconds. How much time does a careful clock on Mercury record, ignoring for the moment Mercury's own motion and focusing on its position near the sun? The answer lands at about 59.9999 seconds. It's another small step away from 60, meaning you'd need 60 million seconds to drift by before the difference reached a single second. 60 million seconds is about 1.9 years. Spread across a lifetime, you're looking at roughly 38 seconds of extra separation, compared with the faraway clock only about 14 seconds more than what we found for Earth. The numbers carry a quiet moral. Time dilation from gravity inside our solar system is real, predictable, and modest. Living on Mercury would not grant an age-defying boon. Your days would still be your days, and the little advantage in accumulated delay, those extra seconds across many years, would be invisible from the inside. From Mercury, Earth would seem to be the place where clocks run slightly faster. Point a telescope home, and, in principle, you would sweep up a few more seconds of Earth's history than you would if you were standing in your old yard. It's a charming thought, but Mercury's scorched surface and thin exosphere keep it safely in the realm of interesting, not practical. The smallness of these solar system effects doesn't make them trivial. It just tells you how gentle our neighborhood truly is. The sun is massive, but not absurdly so. To carve time in ways you would feel in your bones, you need far deeper wells. Neutron stars and black holes, the compact remnants of dead giants, pull with a concentration of gravity that changes the conversation. Near them, the slowing can become dramatic. A clock lowered toward a neutron star would begin to lag in a way you could see with patient instruments. A clock circling a black hole, if it could remain intact, would slow so much that, as it approached certain orbits, outside observers would watch its ticking crawl nearly to a stop. Before leaping to those extremes, it's helpful to linger with perspective. Imagine two twins with identical clocks. One settles near Earth's surface, the other coasts far from any planet or star. When they reunite, it's the Earth-side twin who has felt slightly more of gravity's pull and aged a sliver less. Switch the roles. Put one twin on a station high above, the other on a mountain close to sea level. The higher twin ticks a touch faster because their clock is farther from Earth's center, perched at the edge of a shallower well. These are not paradoxes, but the way the universe keeps accounts. Higher means faster time. Deeper means slower time. Add speed to gravity, and you layer effects. Motion, slowdowns, tug in one direction. Gravitational slowdowns, tug in another. The careful bookkeeping we do for satellites must include both. It's easy to confuse all this with a feeling that time ought to be the same everywhere. Everyday life trains that expectation. What rescues intuition is the constancy of light's speed. To let that speed remain the same for all observers, the universe grants time and space the freedom to adjust. Where mass curves space-time, time ticks at a different rate than it does in flatter regions. Where motion is swift, proper time along that path, the time the traveler carries, unfolds more slowly than the time measured by a resting observer. Put a person on a fast ship and a person in a deep well, and their experiences of a second are honest to each of them, yet not identical when compared. The gentle calculations we've been using hide a practical beauty. If you set two extraordinarily precise clocks on a tall tower, one at the top, one at the bottom, and compare them later, the lower one will have ticked more slowly by a trace. That tiny difference has been measured. It confirms that height in a gravitational field is not just a straight line distance. It's a position in a curved geometry where time's tempo changes. The same insight powered a famous experiment that watched high-energy light fall. A beam of gamma rays sent from the top of a building to the bottom arrived with its peaks squeezed a little closer together exactly as predicted. Think of cars bunching up as a traffic jam thickens a simple image for a subtle truth. Deeper in the well, processes that act like clocks, including the oscillations of light's electric and magnetic fields, appear to run slow when compared to their cousins higher up. Now return to our three stops: Earth, Earth plus the Sun, and Mercury, and keep the numbers in a gentle bundle. Earth alone, 59.99996 seconds for every 60 that pass out in the quiet. A 4-second gap only after about 190 years. Earth in the Sun's embrace, 59.9994 seconds, a 1-second lag every 3 years, adding up to a few dozen seconds across a life. Mercury, closer in, 59.9999 seconds, about 1 second every 1.9 years, or roughly 38 seconds over many decades, some 14 seconds more than Earth. Each step brings you deeper. Each step slows the clock a touch more, but none carries you into fairy tale aging. The lesson isn't that the effect is disappointing. It's that our corner of space is a place of mild curves and generous distances, which is part of why life can organize itself here at all. Where, then, does time's pace truly change in a way that seizes the imagination? At the centers of galaxies live engines, with masses millions to billions of times that of the Sunday. Supermassive black holes shape their surroundings so intensely that orbits near them become a different world. If you could hover just outside the point of no return far enough to avoid falling in, close enough to feel the full depth of the well, your clock would slow dramatically compared with a clock kept far away. To someone watching from a safer distance, your moments would stretch and your signals would arrive increasingly redshifted and delayed. Approach the edge further, and the outside account of your time would approach a standstill. From your point of view, your heart would still beat, your thoughts would still flow, but the comparison would become astonishing. This is the quiet bridge between gentle arithmetic and the grand theater of strong gravity. The same rules that give a 2-second lag in 200 years on Earth also predict the yawning separations near compact objects. The same geometry that widens your field of view at near light speed also explains why light struggling up from a deep well loses energy and shifts color. All of it hangs on a single kindness the universe extends. Keep the speed of light fixed and allow space and time to adapt. When the mass is modest, the adaptation is a whisper. When the mass is overwhelming and concentrated, the adaptation becomes a song you can hear, even if you're only listening with a telescope. Hold the story lightly, and the pieces settle into place. Your own time stays faithful by your side, yet when it's compared with a clock higher from mass, a small lag appears near Earth, a slightly larger one under the Sun's pull, larger still in Mercury's neighborhood. Those shifts won't lengthen a life in any way you'd feel, but they are steady enough to steer satellites, keep networks in step, and probe gravity's shape. Lift your gaze to denser realms, the crowded hearts of galaxies, the remnants of giant stars, and the same rule grows vivid. Time isn't backdrop, but participant, slowing where mass is concentrated, guarding light's promise, weaving clocks and paths and viewpoints into one clean fabric. Carry that rule toward a supermassive black hole, and the texture changes from whisper to chord. From far away, a careful watcher would see you slow and slow again as you skim the deep well, motions that feel ordinary inside turning your head, lifting a hand, stretch into long arcs on a distant clock. Half an hour for you can rhyme with centuries at home. Any signal you send climbs out redder, fainter, each syllable more delayed than the last. Near the boundary where outward light can just no longer escape the event horizon, the outside account of your time slides towards zero. From afar, you seem to pause and dim. From your seat, the crossing brings no theatrics, only the quiet fact that our sturdy equations grow incomplete beyond that edge. What waits inside is still a hushed room of theories. For now, the measurements stop at the horizon, and our math sets down its compass there. Strange as this sounds, it follows the same theme you've already met in subtler settings. Gravity bends space-time. Bend space-time slows clocks. The deeper the bend, the stronger the slowing. Near Earth or Mercury, the effect is a handful of seconds across many years. Near a black hole that weighs millions of suns, the effect swells into something you can feel in your bones if you compare notes with someone far away. The idea does not depend on mystery. It depends on perspective, and on the one stubborn rule that light keeps its speed for everyone. To keep that rule, the universe lets time and space adjust themselves. All of this nudges a quieter question to the front. What is time that it can flow at different rates and hold together with space in such a flexible way? You can't lift it or taste it. You can't set it on a table and look at it from the side, yet it touches every step you take and leans gently on every plan you make. One way to approach it is to build from the ground you know well, directions in ordinary space. Imagine the space around you reduced to its bones. In 3 dimensions, you can move left or right, forward or back, up or down. Those directions are perpendicular pairs, each at a right angle to the others, so that turning fully into one leaves the others behind. Using that simple picture, you can thin space down or thicken it up. Strip away a direction, and you have a 2-dimensional world, a plane with only length and width. Strip away one more and you get a 1-dimensional line, an existence with only this way and that way. No stepping aside, no climbing over. A being born in such a line would know reality as a sequence of points, and a passing photon would be noticed only if it threaded the line exactly. Add directions instead of removing them, and you return to the world you trust, a room with 3 independent ways to move. Perpendicularity is the key. Each new axis must be at a right angle to all the others already present. The brain accepts that for the first 2 additions, draw a line, draw another at right angles, then lift a third out of the page at a right angle to both and balks at the 4th. Within 3-dimensional space, there is no 4th direction that can stand perfectly perpendicular to the existing 3. When artists sketch a cube on paper, they cheat, helpfully. Angled lines hint at depth, and your mind supplies the missing dimension. Mathematicians can do something similar with a shadow of a 4-dimensional shape, a projection that keeps certain relationships intact. The pictures are true to the rules, but can feel slippery to the senses. There is, however, a direction you already move along without choosing. Call it before to after. Unlike left and right, unlike up and down, you don't reverse it at will. Today becomes tomorrow, whether or not you wave your hand. Clocks track that passage with a careful beat. Physics treats that beat as a coordinate, much like the others, but with a special role. When you combine it with space, you get space-time, a fabric woven from 3 spatial axes and 1 temporal axis. In that fabric, Events are points with an address, where and when. The geometry is not the geometry of an ordinary room. Time's axis arrives with a different sign in the equations, which is a mathematical way of saying that turning toward the time axis changes lengths and durations differently than turning toward another spatial axis. But the deeper intuition can be carried without the symbols. Think of a kind of speed budget through space-time. Every massive thing has the same total allowance set by the speed of light and divides it between motion through space and motion through time. When you sit still on a chair, almost your entire budget flows into forward through time. Your heartbeats arrive one after another. The clock ticks steadily. Your position in space barely changes. When you get up and walk, a tiny portion of your budget gets redirected into space. Move faster, and more is redirected. What remains for the march through time becomes slightly smaller. That is a handheld picture of time dilation. Your personal time, the time carried on your wristwatch, stretches compared with someone else's when your motion through space claims more of the shared allowance. At everyday speeds, the difference is microscopic. Near light's pace, the trade becomes dramatic. The geometry makes this precise. World lines tilt, intervals change, lengths in the direction of motion contract. The angles of light's arrival compress forward. But you don't need the angles to keep the feeling. More speed through space, less through time. Light follows its own rule. Being massless, it spends the entire budget on motion through space. In that sense, it has no allowance left to advance through time. That is why, in the clean, cold language of the equations, a photon's proper time between emission and absorption is zero. The idea sounds alien, but carries a simple consequence you've already met. To keep light speed unchanged for everyone, the universe bends distance and duration around it. The payoff is consistency. No matter who measures, no matter how they move, light will not surprise them. Now fold gravity back into this fabric. Mass and energy tell space-time how to curve, and curved space-time tells mass and energy how to move. That single sentence hides a world of effects. Where space-time is curved more strongly, the axis we call time tips relative to the flat regions far away. A clock resting low in a gravitational well is following a path through space-time that gives it fewer seconds between the same pair of events than a clock high up. It is not broken. It is not being slowed by an external hand. It is simply moving along a route where the geometry awards less proper time. Bring two clocks together after they have followed different routes, one deep, one shallow, and you will find the deep one has counted fewer ticks. Tiny differences near Earth, dramatic ones near compact stars, a near standstill at a black hole's horizon as seen from safety. This way of thinking also explains why shapes seem to warp when speeds rise. Consider a fast ship sweeping past a measuring stick laid out along the direction of motion. From the ship's frame, the stick is shorter than the same stick at rest. That isn't an illusion. It is the ship's honest measurement, made with clocks and rulers that have been rotated into space-time's geometry. Distances along the direction of travel contract because synchronized timing between the ends becomes tricky when signals themselves have a fixed speed. Arrange the comparison with care, and everyone agrees on what they measured, even if the numbers differ. No contradictions, just perspectives living in a common fabric. Look back at telescopes and you see the same logic operating under a different light. The James Webb Space Telescope and others before it take advantage of the fact that light needs time to travel. A galaxy seen billions of light years away is being seen as it was billions of years ago. The telescope is not piercing a mist. It is watching an earlier chapter, because those photons left when the universe was younger and have only now arrived. Space-time carries their story forward, respecting the same fixed speed, and in that limit, the telescope becomes a time machine in the most literal, quiet sense. Set these pieces down in a line and they join neatly. Time behaves like another dimension in the way it can be combined with space to form a single geometry. It remains distinct in the way it refuses to be turned back by choice. Moving through space reshapes how you move through time. Gravity curves the fabric and changes the rate at which clocks mark their passage. Light sets the standard pace that everything else must honor. Near a black hole, this geometry is driven hard enough that far-off observers see time itself thin to a thread at the horizon. Inside, our tested equations give way to questions. The singularity suggested by the math, an ultimate concentration where curvature blows up, is a sign that the description is asking for completion. Quantum ideas may smooth the core. New physics may change the script. For now, the horizon is a quiet border between what we can check and what we can only imagine. If the scale of that is dizzying, return to a kinder scale. Feel your own life as a path in space-time, a world line traced by every breath and step. At ordinary speeds and gentle gravitational fields, the fabric is nearly flat. Your watch and your friend's watch remain faithful to one another. Your kitchen table is as long today as it was yesterday. The small exceptions, nanoseconds shaved by flights, tiny shifts in frequency as signals rise and fall, are not intrusions, but confirmations that the rules are present even here, easy to ignore because they are so well behaved. When engineers correct a satellite's clock, they are smoothing the wrinkle made by altitude and speed. When astronomers weigh a cluster of galaxies by watching how its gravity tugs on passing light, they are reading the curvature directly. When someone imagines leaning close to a black hole and then sailing back to a home that has aged beyond recognition, they are telling a story in the same language, only with the curvature turned up until the plot becomes stark. Carry that language forward and time's strangeness softens. It is not a separate river flowing past in different banks. It is one direction in a four-dimensional weave, inseparable from the space it threads, responsive to motion and mass. It can dilate without breaking, contract without lying, and slow to a near halt at the edges of things we are only beginning to understand. You don't need to solve an equation to live inside that understanding. It's enough to remember that every sight is a little old when it reaches you, that your pace through space shares a balance with your pace through time, and that gravity is not a pull from a distance so much as a curve, inviting you to follow. Near a gentle curve, you barely notice you're turning. Near a steep one, you can look back and watch the rest of the universe race ahead. Time plays the role of a fourth direction in the same family as the three we move through every day. That's the heart of Einstein's insight when he joined space and time into space-time. Not two separate realms, but one woven fabric. Think of it the way you think of left, right, up, down, forward, back. Those three are equal as directions. None is more real than another. Time sits beside them in the math, different in character, yet joined so tightly that separating it from space makes the rules fall apart. If the word dimension makes your shoulders tense, soften it into something friendlier, a way to measure change, a way to say where and when something happens without tearing the sentence in two. It helps to start from ground you trust. In three-dimensional life, you can step sideways, climb a stair, or walk across a room. Each turn you make leaves the other turns untouched. A right angle keeps them independent. Strip that world down and you can imagine a flat, two-dimensional life, only length and width, a tabletop realm where above and below do not exist. Thin it further and you land on a one-dimensional line where your whole story runs in a single thread. A being born in that line could never sidestep. All of reality would present itself as a sequence of points, arriving one after another. Now fold in the idea you've been circling, adding a new direction rather than taking one away. Draw a simple map. Compress all of ordinary space into a flat sheet. Call it the XY plane, and reserve a perpendicular axis for time, rising away from the sheet. The sheet holds where, the upward axis holds when. A person, a planet, a photon, any one of them will trace a path in this diagram. For a human, strolling gently, the path is a steady climb. Each tick upward is another moment, another breath. The past sits below your feet on this chart. The future lifts above your head. There's a kindness in picturing it this way because it captures something you already feel. Time seems to flow at a fixed pace for you. You don't reach out and push yourself along the time axis. You rise. Imagine a constant breeze that flows upward in this diagram. You can angle a sail to catch that breeze in different ways. If the sail faces straight into the flow, you rise as fast as possible through time while hardly moving across the sheet. Tilt the sail and you gain sideways motion across the sheet, but you spend part of your breeze on that sideways travel, and your climb through time slows a little. That is a handheld model of relativity. There's a fixed speed woven into the world, the speed of light, and everything you do divides your share of that speed between motion through space and motion through time. A vector, the arrow sailors love to sketch when they talk about wind and course, gives the picture edges. Fix the length of the arrow to represent your full budget, the same for everyone who carries mass. Point it straight up and you're spending the whole budget on time. Rotate it toward the sheet and you tilt some of that budget into space. At walking speeds, the tilt is almost nothing. The arrow still points so strongly upward that your personal time hardly differs from a friend's. Press toward light's pace, and the arrow nearly lies on the sheet. Your motion through space comes at a real cost to your motion through time. That's why, in the honest arithmetic of the universe, fast travelers age less between shared, starting and ending events than those who stayed restful. Their arrows spent more on space and less on time. This way of looking quietly dissolves a stubborn confusion. As you tilt your arrow, your own sense of time does not feel strained. Your watch keeps steady company with your heartbeat. From your point of view, your arrow never stops pointing forward in time. It is the rest of the world that appears altered. Distances along your direction of motion look shorter than they do to people who watched you rush past. Events those people call simultaneous do not line up the same way on your timeline. The model explains why both accounts can be true without fighting. Each observer is slicing the same four-dimensional loaf along a different angle. A playful way to feel this is to populate the chart with simple characters. Lay two little stick figures on the space sheet. Each has the same upward breeze. For a while, both arrows point straight up. Their lives track side by side. The heights of their heads match. Then one figure decides to travel. He tilts his arrow and glides across the sheet while still rising. From his own perspective, he remains upright. Time still points from chest to chin, and space still lies beneath his feet. But to the friend who stayed, the traveler looks different. When the traveler straightens his arrow again and the two compare their heights on the chart, their times, the traveler finds himself a little lower. He has climbed fewer divisions of time, while the sideways motion ate its share of the budget. The surprise deepens if you add a simple projection trick. Have each figure, at intervals, carry a lantern that casts a ghost of their shape onto the other's space sheet. While both arrows point straight up, the shadows look familiar. As the traveler tilts and begins to move quickly across the sheet, his shadow changes shape. From the homebody's perspective, the traveler seems to flatten along the direction of travel. This isn't a magic mirror. It is a way to see length contraction in a friendly drawing. At high speed, distances measured along the direction of motion shrink for the traveler. The flattening is not a mistake. It is the honest report of measurements made with clocks and rulers that have been rotated in space-time. A common question slips in. If time is just another direction, why can't you turn and look along it the way you look down a corridor? The chart answers without scolding. Turning from left to right leaves you inside the same space. Turning toward the time axis is not that kind of turn. The geometry of space-time isn't Euclid's classroom. In the equations, time carries a different sign, and that sign encodes the boundary between motions possible for massive things and motions reserved for light. A full right-angle pivot into the sheet is a rotation you can perform. A full right-angle pivot into pure time or into pure space beyond light speed is not available to you if you carry mass, because the fixed-length arrow, the speed of causality, doesn't stretch. The budget is constant. How you apportion it is your only freedom. Keep the sail and breeze picture a bit longer, and a few more familiar effects slip into view. Two travelers moving fast relative to each other will disagree about the now slice that passes through the same distant mountain. To one, a lantern flickers on the hillside. At the same moment, a bell rings in the square. To the other, those events come in a different order. This relativity of simultaneity is the partner of time dilation and length contraction. It is not a paradox. Only the way angled slices through a shared loaf produce different cross-sections. The loaf is one loaf. The events fixed inside it, the slices, and the stories we tell from them depend on motion. The language of vectors makes room for light as well. A photon doesn't carry mass, so it spends the entire budget on motion through space. In our chart, its arrow lies flat along the sheet. Because it lies flat, it does not climb in the vertical direction. In the precise bookkeeping of the theory, the proper time along a photon's path is 0. That sentence sounds cold but carries a warm consequence. The universe keeps light speed the same for everyone by letting time and space bend around it. Distances and durations change so that the arrow for light never changes length. In your everyday life, that rule shows up as small corrections to satellite clocks. In stronger fields and faster flights, it becomes the headline. Gravity fits into the same picture by curving the chart. The breeze still blows upward, but the grid you used to trust has been gently reshaped by mass and energy. What looked like straight vertical lines now lean and bow. the shortest paths between points. Geodesics aren't straight in the old sense. Place a clock near a large mass, and its arrow follows a route that yields fewer ticks between the same two events than the route followed by a clock far away. This isn't a friction that slows the clock. It's geometry, asking different paths to trade different amounts of the budget between space and time. Lower, deeper paths give less proper time. Higher, gentler paths give more. A tower-top clock ticks a little faster than its basement twin, and a satellite's clock needs steady care so navigation stays faithful. Return to the two figures and draw one more scene. Let them start together. One tilts and glides for a while at a speed most of us only imagine, then straightens and meets the friend again. They compare notes. The traveling one has aged less. The friend, who stood upright with his arrow mostly vertical, has climbed farther. The difference isn't a trick, isn't a metaphysical quirk. It is the bookkeeping of a constant budget and the angles chosen along the way. The traveler's world also looked differently shaped. While he moved, distances contracted along his path. Clocks on the sidelines appeared slow. Now, surfaces tilted. Those observations are symmetrical. Each can say them about the other during uniform motion. The moment they reunite, the histories they carried are not symmetrical because their paths through the curved fabric were not the same. There's a quiet comfort in how the model places things you've heard into a single, gentle frame. The flattening of fast-moving objects in the direction of travel is not a painter's illusion. It's the projection of a rotated shape in a geometry that blends space and time. The slowing of a moving clock is not a betrayal of the clock. It's the cost of spending more of the budget on space. The inability to look down time like a hallway is not a blind spot. It's the mark of time's distinct role in the fabric. The fixed speed of light is not an arbitrary rule. It's the length of the arrow that sets the budget for everyone and keeps cause linked to effect. If you picture the chart long enough, other corners of physics feel less sharp. A telescope looking deep into space truly peers into the past because the arrows of ancient light lay flat along the sheet for an enormous distance before meeting our upward climb. A spacecraft falling toward a massive planet follows a path that makes the most of the local geometry, the way a bead finds the bottom of a curved wire. A beam of light climbing out of a gravitational well loses frequency as if it were running uphill against the geometry, arriving redder than when it began. None of these require new rule. They're all shadows of the same arrangement. What this model doesn't do is turn time into something you can pivot into at will. The breeze keeps you rising. Your choices tilt the sail. You can spend more of the budget on motion through space and, in so doing, slow your climb through time compared with someone else. You can climb where the grid is flat and gather more proper time, or you can dwell where the grid is curved and accept fewer ticks for the same landmarks. And you can understand why. In strong fields, the shapes on the chart buckle so intensely that beyond certain edges, the horizons we talk about, with careful voices, the familiar coordinates themselves stop behaving like helpful guides. Hold the picture softly, a flat sheet for the places you can walk, a clean axis for the moments you live, an arrow that keeps its length and shares itself between the two. At low speeds, almost all of it points upward. At high speeds, more points across. For light, all of it lies in the sheet. Add mass, and the grid curves, inviting arrows to follow new lines. Add two travelers, and you get different heights when they meet again. Not because anyone cheated, but because their paths were different. Add an outside observer, and you get flattening along the motion. Not because objects truly change their nature, but because measuring rods and synchronized clocks have been rotated in a shared geometry. The appeal of calling time a dimension is not about abstract prestige. It's about making sense of these linked effects without strain. When the mind holds space and time as partners, the strange becomes coherent. Moving fast trades time for distance. Gravity tilts the grid. Photographs of high-speed travelers look foreshortened. Clocks deep in a well lag. Light refuses to change its speed, and so everything else must accommodate it. Your life stays ordinary, even as the universe reveals this deeper weave. You still pour tea and hear it cool. You still fall asleep and wake. Underneath, a constant arrow points, divides its budget, and writes a path in a quiet diagram where every event has an address and every story fits without a seam. From the traveler's seat, nothing about their own shape seems to change. The chest still faces forward in time. The heartbeat keeps steady count, and the body feels as solid as ever. What shifts is the rest of reality. Edges of the scene seem to pull and stretch, as if the horizon itself were being drawn inward. The destination appears farther than memory says it ought to be. Objects aligned with the path look subtly compressed, while structures off to the sides feel poured toward the center of vision. That's exactly what a space-time picture would whisper. When your arrow tilts toward motion through space, your measurements of distance and duration rotate with it. The old classroom sketch of flattening is not the traveler's self-portrait. It's the shadow cast in someone else's frame, a projection of a rotated shape. In a two-dimensional demonstration, you only see one direction squeezed. In the full three-dimensional world, the squeeze shows up along two perpendicular directions across the line of travel, a more generous distortion that still points to the same underlying cause. If time truly behaves as a direction, the thought opens doors and draws new questions in the same breath. What provides the steady push that carries everything forward? Why can we tilt our arrow to spend more of the budget on space, yet never aim it cleanly downward into the past? The diagram allows such a tilt in principle, but nature seems to forbid it for massive travelers. That asymmetry is part of the fabric bound to causality, to the way light sets the limit for signals, to the thermodynamic story of disorder that prefers one temporal orientation over the other. The model also nudges at a quieter curiosity. If time is a direction, do we have any thick extension along it, the way a tree has thickness in space? Or are we thin, like coins held edge on? The simple picture leans toward thin. We look full and round when seen head-on within space, but turn the viewpoint toward time and we present very little depth. If there's almost no thickness to catch the eye, no wonder we cannot see through time. There simply isn't enough of us to show. It's only a model, but models can be helpful when they explain the familiar without strain and predict the unfamiliar with a light touch. This one organizes several phenomena that otherwise feel scattered. Why fast travelers age less between agreed-upon meetings, why lengths along the line of motion contract, why simultaneity refuses to be universal, why clocks deeper in gravity's well tick fewer beats for the same landmarks than clocks higher up. It also harmonizes with the simplest rule of all. The speed of light is the same for everyone, and the fabric bends other quantities to keep that promise. That last statement sounds reassuring, and then Light, being light, finds ways to complicate our comfort. Everywhere you look, light behaves as if it enjoys keeping us slightly off balance. Ask whether it is a wave or a particle, and it answers yes, with experiments that reveal different facets depending on how you ask the question. Measure its speed, and it recites the same number, 299,792,458 meters per second, no matter who holds the ruler or how fast they're moving, so long as the measurement is made in the emptiness of a vacuum. Two observers may slide past one another, one ambling at a percent of light's pace, the other rushing at half that cosmic limit. If both watch the same beam of photons, both report the same speed. To preserve that agreement, space and time adjust, bending distances and intervals, rather than allowing the beam to be seen as anything but itself. Then come the caveats, honest and well understood. Light traveling through matter is not truly free. It interacts with the medium. In air, its progress is slightly slower than in a vacuum. In water, slower still. In glass, slower by more. The numbers roughly 225 million meters per second for water, about 200 million for common glass, aren't secrets, but the signature of a process. An electromagnetic wave passing through a material stirs the charges inside. Electrons jiggle in response, like floats on a choppy sea. Those moving charges radiate in turn, creating a secondary wave that overlaps the original. Where the two overlap, the crests and troughs don't simply add, they interfere, sometimes lifting one another, sometimes pressing one another down. The combined pattern, averaged across many atoms, marches forward with a new effective speed. Step back out into empty space, and the agitation ends. The original wave continues in freedom at the vacuum speed again. No rules are broken. The medium simply makes light spend time in detours and local exchanges before the overall pattern emerges on the far side. That explanation comforts and holds together until experiments invite us to look more closely at how light threads its way through space and time. Certain modern twists on the classic double-slit arrangement and related interferometry tricks suggest a picture that's stranger to the ear than to the math. Prepare paths that differ in length or material, and you can coax photons to arrive in step or out of step at the finish, even when one route seems slower on paper. Tally the detections, and the pattern implies that some of light's amplitude explored several possibilities, as if parts of the wave function felt both routes and interfered with itself. Describe that in everyday words, and it sounds as though light took shortcuts or lingered, sometimes appearing to travel faster or slower than the vacuum limit. Describe it with care, and you recover a gentler truth. The final detections land on the same coordinates in space and time that a consistent calculation predicts. Where speed seems to wobble, what's actually wobbling is the path's composition, the fraction of the journey spent in media, the phase shifts along the way many possible histories add and cancel. The vacuum rule stays intact. The rest is the choreography of interference. Seen from the space-time chart, this choreography looks less like a rebellion and more like a dance in a crowded room. The arrow for light lies flat along the sheet of space, but when the sheet is filled with matter, the route is not a straight line through emptiness. The field excites charges, which exchange energy with the wave, which produces delays and phase advances that you can fold into an effective index of refraction. Mathematically, you sum an infinity of tiny processes: absorption and re-emission, polarization responses, collective oscillations, and out comes a clean result, a pulse that crosses the material at a reduced group velocity, emerging later than it would have had the room been empty. The instant it re-enters vacuum, the speed snaps back to C. The fabric has not failed. It has asked the traveler to navigate a maze of handshakes before returning to the open road. Interference does more than retime pulses. It paints shapes on screens and makes hard edges soft. In the double-slit arrangement, a single photon leaves a source, drifts toward a barrier with two narrow openings, and registers on a detector beyond. Repeat that experiment one photon at a time, and patterns emerge that reveal wave behavior. Close one slit, and the pattern changes. Put detectors at the slits to watch which opening the photon chooses, and the interference diminishes. It isn't that light decides based on our curiosity. It's that the full experimental setup, sources, paths, detectors, determines which quantities can interfere and which are nailed down by measurement. The space-time picture still holds. Every detection is an event with a where and a when. The oddness comes from the way quantum rules distribute amplitude among possible paths, and then let those possibilities combine. Gather these strands and the earlier model of time as a direction grows richer. The traveler who tilts their arrow and watches the world stretch at the edges is not imagining things. Aberration, Doppler shifts, and length contraction are what you would expect from a rotated slice through a shared geometry. The outsider who sees the traveler flattened along the line of motion is not fooled by a trick of sight. Their synchronized clocks and laid-down rulers genuinely report that contraction. The gravitational well that appears to thicken time and redshift light is not imposing a drag. It is curving the grid, tilting the time axis, and making certain paths yield fewer ticks between markers. And light, the envoy of causality, threads all of this with its own peculiar rules, always respecting the vacuum limit while showing endless subtlety in how it moves through matter and superposes possibilities. Consider gently what it means for experience. If you ride fast, you do not feel yourself becoming a sheet of paper. Your own time remains your measure, and your cabin's ruler remains your standard. From your seat, it is the distant clock that runs oddly, the distant meter that takes on new lengths. If you stand still and watch a swift craft pass, instruments in your frame tell a consistent story. Its time is dilated, its lengths along the motion contracted. Both stories are true because they are statements about relations, not about absolute qualities. When you reconcile them, you return to the diagram with its fixed length arrow and its stern rule for light. The asymmetry along time's direction remains the quiet puzzle that stirs at the edge of these tidy pictures. You can tip your arrow within the cone allowed by causality. You cannot turn it downward, past the horizontal, and sail into yesterday. Microscopic laws often look reversible on paper. Macroscopic experience points one way. Somewhere between those scales lies the thermodynamic arrow, tied to the rise of disorder, the flow of heat, the fact that scrambled eggs do not leap back into a shell. Whether that arrow arises from boundary conditions in the early universe or from the way information spreads and becomes inaccessible, the effect in your hands is the same. The breeze lifts you toward the future, not the past, and your choices are about how much of the budget to spend on space along the way. If If you picture yourself as a thin coin in the fourth direction, it clarifies one last thing. We don't peer through time because we don't extend enough in that direction for our senses to catch. We are richly structured in space, organs, bones, nerves, but in time, we are traced as a path, not printed as a block. Instruments can compare paths. Physics can predict how much proper time your arrow will gather between two agreed events. Telescopes can look back by catching light that left long ago. But eyes cannot swivel to take in a thickness we do not possess. We meet moments as they arrive, and the model's job is to make peace with that while still explaining why a satellite's clock needs correction, why a muon created high in the atmosphere lives long enough to reach the ground, why a star's light is delayed and reddened when it skims a massive body on its way to us. Meanwhile, even when you let go of the numbers, the behavior of light and matter keeps the story grounded in things you can feel. A straw looks bent in a glass because the wave slows in water, altering its direction as it crosses the boundary. A prism spreads white light into colors because different wavelengths stir electrons differently and therefore advance with slightly different effective speeds, splintering the beam by phase. Fiber optic cables guide pulses around the world by taming those interactions, so the group of waves that carries information keeps its shape. Each of these daily scale effects is the gentle cousin of the deeper claims. Space-time sets the stage. Light plays by its rules. Matter collaborates by responding to fields in ways that can be tuned and predicted. So the model that began with a flat sheet for space and a clean axis for time does more than soothe a restless idea. It becomes a small workshop where you can set down familiar pieces, aging twins, flattened rulers, blue-shifted starlight, clocks in towers, photons in glass, and see that they belong to the same set. From the traveler's unbothered body to the outsider's foreshortened view, from the question about a push upward along time to the quiet answer about causality and heat, from the stubborn constancy of light in a vacuum to the patient delays inside matter, the theme stays kind. Space and time share a budget. Motion and mass change how that budget is spent. Light fixes the scale and insists on consistency. The rest is perspective, interference, and geometry weaving themselves into the calm night we live in, where even the strangest ideas can be carried like a soft lantern from one thought to the next. In a quiet lab at Harvard a generation ago, a beam of light was persuaded to slow to the pace of a bicycle. A cloud of sodium atoms, cooled to a breath above absolute zero, was tuned until it behaved like a new kind of medium, transparent yet exquisitely responsive, so that a pulse entering it crept along at about 61 kilometers an hour. Later, the same technique learned a gentler trick. Bring the pulse to a full stop. Store its pattern inside the cloud like a pressed flower, then warm the atoms and let the pulse resume its way, as though time inside the medium had been folded and kept safe. Strange as that sounds, the rules of light did not break. The medium simply borrowed the pulse's information and carried it for a while, like hands relaying a candle along a darkened aisle. Strange things also happen in the other direction. In another experiment, a brief pulse crossed a tailored cloud and seemed to appear at the exit before the main body had fully entered. Timing plots drew a mischievous picture, an early peek at the far side, as if the pulse were leaving before arriving. It is tempting to imagine causality being teased, but the rescue is kind. Once you remember that a pulse is not a single pebble, it is a shape, a packet with a front and a tail, built from many frequencies. The medium can reshape that packet, amplifying the earlier parts and trimming the later ones, so the maximum of the hump pops out ahead. No single photon has outrun itself. The packet's profile has been edited by the material. Information, the earliest whisper above silence, remains faithful to light's limit. It helps to hold 3 speeds in your palm. Inside the packet, little crests and troughs zip along. Their rate is the phase velocity. The packet as a whole, the envelope that carries a blink or a beat, moves with the group velocity. The very first nudge that a signal has begun is tied to the wavefront velocity. A stadium shows you the difference without any equations. Start a crowd and watch a ripple of upraised hands sweep section to section. The ripple seems to race even though the fans never leave their seats. That shimmering motion is like phase. The people themselves are like the group. The first person to stand at the leading edge is the wavefront. No matter how wildly the arms wave, you cannot deliver a message to the far end of the stadium faster than a person can carry it. That gap between how a wave looks and how a message travels opens the door to a quieter marvel. The familiar double-slit arrangement paints bright and dark bands because a wave can take 2 paths at once and combine with itself. Recently, the slits were not cut in space at all, but opened and closed in time. A thin film, an indium tin oxide layer, like the ones that live under your fingertips and touchscreens, was driven with an ultra-fast pulse, so that its optical properties flipped for a fleeting instant, from transparent to reflective and back again. For a few femtoseconds, there was a mirror where a window had been. Send a laser pulse against that film, and you can catch the momentary reflection. Send 2 pulses in swift succession, and something uncanny appears. A pattern of frequencies, bright and dim, like stripes, but not across the screen, across the spectrum. Instead of spatial interference, you get temporal interference. The wave has met a pair of slits in time. A picture helps. Draw a simple graph, space running along the horizontal and time climbing upward. A photon leaves a source, travels to the film, meets a moment when the film is reflective, and bounces back to be recorded. A second photon is sent a breath later and meets the second reflective moment higher up on the time axis. If nothing more were at play, you would simply record 2 reflections arriving at 2 slightly different times. But a wave is allowed to explore possibilities. With 2 temporal openings, parts of the field that interact at the first instant and parts that interact at the second instant overlap when they reach the detector. Where their phases line up, certain colors are strengthened. Where they oppose, those colors fade. On a spectrometer, the dance looks like teeth, evenly spaced in frequency, the signature of a double slit, drawn not in space, but in time. This is where the earlier talk of phase and group becomes more than vocabulary. A pulse contains many colors packed together. A sharp change in a material's properties is like plucking a string. It spreads the tone. When 2 such plucks happen in rapid succession, their tones superpose. At some frequencies, the peaks of one meet the peaks of the other, and the result grows. At others, they cancel like overlapping ripples. Temporal gating chops the pulse into pieces that later recombine, and the recombination writes a comb onto the spectrum. You are not bending causality. You are giving the wave 2 instants to respond and watching how those responses add. Returning to the worry about faster than light, the rescue is still the same. Even when timing tricks in exotic media make a pulse's peak jump forward, the front of the packet, the earliest new information, keeps to the rule. Think again of the crowd. A clever coach can choreograph the cheering so that the tallest burst appears in the next section before the previous section has fully quieted, but no cheer is heard beyond the furthest fan until the walkers arrive. In light and matter systems, the medium can be prepared so that energy stored inside it and the incoming wave conspire to reshape the envelope, yet nothing outruns the wavefront in a vacuum. The invariant number that relativity guards remains the horizon for influence. These laboratory stories are gentler when folded back into the model where time is a direction. A temporal slit is simply the time axis cousin of a spatial aperture. Restrict axis in space, and the wave spreads in angle. Restrict axis in time, and the wave spreads in color. In a space-time diagram, one looks like a pattern written sideways, the other like a pattern written upward. Both remind you that a photon is more than a marble. It is a disturbance, extended in space and in time, sensitive to boundaries of either kind. When the boundary is a window that opens briefly, you carve the wave along the time axis and the spectrum bears the mark. It also softens the alarm that words like stopped light and superluminal pulse tend to trigger. The fixed speed that relativity protects is not the pace of every pattern that happens to involve light. It is the speed that connects causes to effects in empty space and sets the slope of the light cones inside which influence must travel. Place light and matter, and you invite new actors, electrons, lattice vibrations, collective modes to trade energy with it. Those trades show up as delays, advances, phase slips, and reshaped envelopes. Step back into vacuum, and the traveler regains the open road at the same old speed. On a night when sleep comes slowly, there is comfort in one more image. Picture a stream running through a meadow. In the open, the water finds its easy pace and keeps it. Thread that stream through reeds and it slows not because the water forgets how to flow, but because the path now includes 1,000 small touches. Widen the channel suddenly, and ripples race out. Narrow it twice in quick succession, and ripples from both constrictions meet and make patterns. Far downstream, the current returns to its old certainty, as if nothing odd ever happened. Light behaves that way in media. It lingers, it exchanges, it knits interference where boundaries are sharp in time or in space. Then, free of the reeds, it resumes the glide that defines causality for everyone. Set the images aside and the thread remains clear. A cloud crafted near absolute zero can coax a pulse to creep or pause because the atoms in the field exchange energy in an orderly, reversible way. A different medium can reshape a packet so the moment of maximum arrives early, without any single photon breaking the limit that protects cause and effect. A pulse is built from many frequencies. A rapid change in a material's properties spreads and rearranges those frequencies. Two such changes close together draw an interference comb across the spectrum. A spatial slit writes bright and dark on a wall. A temporal slit writes bright and dim in color. Across all of it, the most faithful rule remains quietly in place. New information does not arrive sooner than light traveling in empty space could carry it. And so, the tale loops back to the gentlest beginning. Light is not only a messenger across distance, it is a patient recorder of history. It remembers the texture of the road, the pauses and handoffs, the sudden gates that opened and closed in time, and it lets those memories show up as shifts in hue and shape at the end. Hold that picture for a while, and the strangeness loses its sting. The universe is not breaking its promises. It is keeping them in a larger room where space and time are directions of one fabric, and where boundaries drawn in either place write their quiet signatures on what we see. Picture a simple timeline drawn in black, a quiet ruler for when each crest of a light wave that reaches the detector is a small tick, a hello, arriving at regular intervals. Now tilt the incoming wave slightly in time, open and close that reflective window, a whisper sooner or later, and the ticks step closer together. Peaks arrive more often. To your ear, that would be like raising a note. To your eye, it becomes a shift toward blue. Color, after all, is only frequency made visible. Lower frequency feels warmer and redder. Higher frequency feels cooler and bluer. So far, the story is calm. Nudge the timing, and the spectrum slides. What feels less calm, at least in the drawing, is what those angled paths seem to say. In the sketch, straight lines stand for light cruising at its inviolate pace in a vacuum. But the moment you let the mirror exist only for a fleeting instant, some of the drawn paths look as if parts of the journey take longer than expected, like light has dawdled, while other parts look as if the drawing has allowed a leap, the kind that would be forbidden if taken literally. The temptation is to think, is this photon, for a breath, going backward in time? The right response is gentler. A photon is not a tiny marble that picks one precise curve and sticks to it like a train on a track. It is a quantum object with a spread of possibilities described by a wave function. And when a boundary opens in time, as well as in space, that spread gets carved and recombined. The sketch records that carving and recombination as slanted lines. The math is precise. The picture is a metaphor. There is a helpful principle that threads through these puzzles. Among all available routes, light behaves as if it chooses the one that makes the travel time stationary, not necessarily the shortest distance, but the path of least time when all influences are counted in empty space that reduces to a straight line at a fixed speed. In glass or cold atomic clouds, the medium joins the conversation. Delays and phase shifts become part of the terrain, like stretches of road with different surfaces. When you flip a material from transparent to reflective for 2 brief instants, you are drawing 2 gates on the time axis. The wave samples both gates. Parts that reflect at the first gate and parts that reflect at the second arrive together and interfere. The interference appears not as bright and dark stripes on a wall, but as comb teeth in color, some frequencies reinforced, others thinned. If you try to translate those comb teeth into a literal travel diary, you will tie yourself in knots and start inventing paradoxes that the experiment does not require. The wavefront, the very first detectable change from silence, still respects the limit that protects cause and effect. Group velocities can be pushed around by clever materials. Phase velocities can be coaxed into numerology that looks outrageous. Envelopes can be reshaped so the peak sneaks out early. None of that moves a genuine message into the past. The interference tells you that different time slices of the field are overlapping at the detector. It does not tell you that a single photon drove the wrong way down the one-way street of causality. A softer way to carry the idea is to use lightning as a picture. In a storm, you sometimes see faint tendrils reach toward the ground before the main bolt strikes. They are not the strike, but they are part of how the strike finds the path it will take. In the quantum world, Feynman's sum over histories says something similar with equations. To predict what you'll detect, you add contributions from all possible paths, each weighted by a kind of internal rhythm. Most cancel, a few reinforce. The path of stationary time emerges from that sum, not from a marble picking the right line in advance. When you open slits in time, you are changing which contributions arrive in step. The drawing with slanted lines is a child's version of that adult calculation, evocative but not literal. If the picture can hint at backward travel, it opens the door to a harder question that has played like a melody under modern physics. Can information move backward in time? In ordinary life, the answer is plain. Dinners cannot be uneaten. Spilled water does not leap back into a glass. The road behind the car remains behind. The paradoxes that would follow a yes lotteries, warnings, the undoing of choices, would shred the quiet logic that keeps days coherent. So we say no, and we live in peace. Zoom in far enough, though, and the world becomes surprisingly talkative across distance. Two particles can be made in a way that links their properties so tightly that measurements on one tell you what a measurement on the other would show, no matter how far apart they fly before you check. That link is entanglement. You need no fanciful language to describe it. Make a pair with equal and opposite momenta, and if you later find one moving left, you know the other must be moving right, so the total still adds to zero. Do the same with spin, or polarization, or other paired quantities, and a similar constraint holds. For a while, even thoughtful people tried to make this seem ordinary. Perhaps the particles carried secret instructions, a script they agreed upon at creation. When you measure one, you reveal a property that was there all along, and the other simply reads the complementary line. That picture is comforting and wrong. Experiments that close clever loopholes show that no script written in advance can explain how often the correlations line up the way they do. The results violate inequalities that any hidden instruction theory would have to respect. The particles do not carry pre-stamped answers to every question. They carry a joint state that refuses to split into separate inventories. When you measure one, you get a definite result, and the shared state collapses into a form that makes the other's outcome correlate with yours in a way that a script could not have guaranteed. It can feel, in a sloppy sentence, like the first measurement reached across space and whispered to the partner, or, if you play with delayed choices, like it reached backward in time, but careful language rescues you again. No usable message rides on those whispers. You cannot arrange the settings and outcomes on your side to force a chosen message onto the other side. The statistics conspire to keep signals inside the light cone. That conspiracy has a formal name, the no-signaling theorem, and a simple moral. Quantum correlations are sturdy and strange, but they are not telegraphs. Even the famous delayed choice and quantum eraser games, in which you decide late which kind of pattern to look for, do not send a note into yesterday. They sharpen the sense that what counts as a path depends on the entire experimental arrangement, but they never let you encode, transmit, and read a coherent sentence faster than light or backward in time. If you arrange things so that which path information is available in principle, the interference dissolves. Arrange things so that which path information is erased in principle, and interference returns in certain combined records. The drama lives in the bookkeeping of possibilities, not in a wire strung from future to past. fold these quantum threads back into the space-time picture you've been carrying. A direction in time is not a hallway you can walk down and shout through. It is an axis in a geometry that sets how intervals and distances behave. Light defines the slope of the cones inside, which cause, can, influence, effect. Entanglement knits distant points together not by a wire, but by a shared description that cannot be pulled apart into local pieces. Temporal slits carve a pulse along the when-axis, the way spatial slits carve a wave along the where-axis. And in both cases, the pattern you see is a poem written by interference. Group velocities can exceed or lag behind the vacuum standard in crafted media, but the first telltale rise from zero, where new information enters, stays within the cones. The calm remains. The world does not allow you to outrun the limit that keeps stories consistent. There is one more way to soothe the discomfort that drawings of backward paths can provoke. Those angled lines in the sketch are not photons being rebellious. They are a shorthand for phase. When a material's properties change quickly, the phase of different frequency components is kicked by different amounts. At the detector, the total field is the sum of all those components. Where they add in step, the spectrum brightens. Where they oppose, it dims. The apparent leap in arrival time of a peak is the place where those components happen to align strongly again after being retuned by the gates in time. If you were to hide the clock and watch only the earliest hint that anything at all had changed, you would see nothing premature. And so the initial puzzle, the feeling that light tests other routes through time, finds a gentler phrasing. Light explores possibilities in the only way quantum objects can, by having amplitudes for many paths, amplitudes that combine. No single photon is caught visiting yesterday. Instead, when you allow two instants to matter rather than one, you invite those amplitudes to overlap in a way that writes stripes in frequency. It is not lightning discovering the ground by touching it. It is lightning finding the path by feeling in the air. The last question, the one that leans close to the pillow at night, is whether any of this changes the arrow of time you live by, not in the way a science fiction story might wish. The one-way push you feel is anchored not only in causality but in the way disorder grows. Heat moves from hot to cold. Friction eats the neatness of motions. Memories accumulate in one direction because the world has many more ways to be jumbled than to be pristine. Microscopic laws admit time-reverse solutions on paper, but the boundary conditions of our universe gave us a low entropy beginning, and the tide has been rising ever since. Against that tide, the most precise clocks still disagree by tiny amounts because of speed and gravity. The most delicate pulses still knit and unknit under temporal gates. The strongest correlations still refuse to carry a message through forbidden corridors. All of these are notes in the same quiet score. If you keep the score in mind, the mind-bending becomes bearable. A black line for time, a few slanted paths for light shaped by materials, comb teeth in a spectrum where once there was a single tone, two particles sharing a state that cannot be split. The constants stay constant. The limits keep their shape. The surprises live not in rules being broken, but in how wide the room is in which the rules can play. And there, in that wide room, is the kindness of the whole enterprise. You can drift to sleep, knowing that the universe remains consistent, even when it leans into wonder. That light keeps its promise even when it seems to wink. that time remains a direction in which stories unfold, with all their odd turns and steady beats, and that our task is only to listen carefully enough to hear the pattern without forcing it to be simpler than it is. Begin with a pair made together. Like twins who share a secret rhythm, they fly apart, quiet and small, each carrying the possibility of many futures. That's the stage for Bell's idea. He wondered whether these twins' entangled particles were simply revealing a script they'd tucked in their pockets at birth, or whether they truly kept their options open until the instant someone asked a question of them. Hidden variables were the tidy dream, little note cards with answers for every direction you might care to measure. Quantum mechanics told a different bedtime story. No note cards, just a shared state that refuses to split into separate parts, and answers that crystallize only when you look. Spin is the property used as the lantern in this story, and the name can mislead. Nothing here is literally whirling like a top. Spin, in this context, tells you how a particle responds to a magnetic field. Up and down are simply two opposite outcomes along a chosen direction. Take two particles born together so that their total spin sums to 0. Measure both along the same direction, and you will always find opposite results. If one registers up, the other must be down. That perfect opposition isn't the argument. Both the tidy dream and the quantum story make that same promise. The question hides at a slant. What happens when you tilt the detectors and ask about different directions? Bell found a way to turn that question into a wager. Imagine that for each particle you could choose among several detector settings. 3 will do for a clear picture, and for each setting, the detector reports either up or down. If the world follows the tidy dream, each particle carries a fixed table of answers for all 3 possibilities, written at birth. They may be opposite tables, one up where the other is down to preserve the 0 total, but they are tables all the same. If instead the quantum story is right, there is no table until you ask. The shared state only guarantees the opposite result when the same direction is asked on both sides. For mismatched directions, it gives you only probabilities. Now sew the math into something you can hold. Suppose you choose directions at random on each side. When the same setting happens to be chosen for both particles, opposite outcomes are guaranteed. Full stop. When different settings happen to be chosen, the tidy dream and the quantum story disagree about how often the 2 sides will match. Hidden variable tables put a floor under the matching rate. If you work through the possibilities carefully, you find that, averaged over many trials and ignoring the cases where the settings matched, outcomes from different settings will still agree at least 55% of the time. Quantum mechanics, by contrast, insists that for certain angles, the agreement will hover near 50%, no preference, just a coin flip's fairness. The 5 percentage points between those predictions sound small, but they are a chisel. With enough trials, the chisel can cleave cleanly between the 2 worlds. Picture the experiment as a quiet assembly line. A source produces entangled pairs and fires them in opposite directions toward 2 stations. Each station independently and randomly picks one of the allowed detector angles, records up or down, and notes which angle it chose. No cue travels from one station to the other. They are too far apart and too fast for any ordinary message to slip between them in time. After many pairs, the notes are brought together. You sort the data into piles: cases where the settings matched, cases where they differed, The matched pile behaves as promised. Perfect opposition. The mismatched pile is where the wager is paid. Time and again, the tallies settle near the quantum number, not the tidy dreams. The cleanest versions of these tests close sneaky loopholes. No post-selection, no side channels, random choices shielded from influence, and the line still falls where quantum mechanics said it would. There's a gentle shock in that result. It says the world does not carry a pre-written column of answers for every question you might ask. The answers are not revealed, they are realized in the act of measuring, yet realized in a way that keeps the two far-flung stations in step beyond what any hidden script could account for. Call that spooky if you like. Even Einstein did. But be careful with the spookiness. Nothing in those tallies lets you whisper a chosen message to the other side. You cannot decide to force up here and thus compel down there. The statistics on either side, taken alone, are always blandly 50-50. Only when you bring the notebooks together and compare do the correlations bloom. That quiet fact, the no-signaling theorem, dressed down into plain speech, keeps causality safe, even as correlations laugh at distance. If the picture still feels slippery, it can help to trade the algebra for a story with lanterns and windows. Imagine each detector setting as a different tint of glass, and up or down as which window the photon prefers to exit. The hidden variable dream says the photon carries a secret instruction sheet. If the glass is tint A, exit left. If tint B, exit right. If tint C, exit left. Its partner carries the opposite sheet, so that when the same tint is used on both sides, they exit opposite windows. Run the experiment many times with randomly chosen tints, and the overlap of instruction sheets forces a certain minimum of agreement even when the tints differ. Quantum mechanics says there are no sheets. Instead, the pair shares a state that only yields definite exits when a specific tint is chosen. Choose different tints on each side, and the shared state yields statistics that settle closer to 50-50 than the instruction sheets allow. Build the apparatus, watch the exits, and you see the shared state's signature, not the fictional sheets. One of the kindest ways to make peace with this is to think in terms of geometry rather than hidden messages. The correlations are not a telephone call. They are the shape of the state itself. A circle, drawn on a page, has properties every diameter splits the circle in half that do not require any point on the circle to know about any other point. Entangled states have geometric relations written into them in the same quiet way. When you cut across the state with a particular measurement, pick a detector angle, you reveal one of those relations. Cut across with a different angle on the other side, and you reveal a relation between different slices. The strength of the correlations depends on the angle between those slices. Bell's inequality is a claim about how strong those relations could be if the state were just two local sheets of instructions. The experiments show the circle is not two sheets. It is the larger shape. Why does the mismatch between 55% and 50% matter so much? Because it is not a quirk of a particular apparatus or a miscalibrated magnet. It is a crisp boundary between two ways of imagining reality. If the hidden variable story were true in the simple sense, each particle carries definite properties that exist regardless of being measured, and those properties are set locally at the source, then no matter how clever you get, your tallies cannot cross that line. The fact that the line is crossed means at least one comforting assumption must be abandoned. You can keep locality, but give up the idea that properties exist before measurement in the way classical objects do. Or You can keep pre-existing properties but admit influences that are non-local in a way classical locality forbids. Quantum mechanics chooses the former. Properties live as possibilities until measurement. The joint state encodes relations that are real and testable, and causality, as far as sending messages is concerned, remains intact. The strangeness blooms brighter when you play with time in the setup. There are versions of the experiment in which the choice of detector angles is made so late that, by ordinary reckoning, the particles could not have known which questions would be asked when they left the source. There are versions in which entanglement is created after the particles have been measured, by cleverly post-selecting and recombining records, an arrangement with the friendly name entanglement swapping. The correlations still appear, wearing the same quantum signature. A hasty storyteller will say the choice reached backward in time to rewrite outcomes. A kinder narrator notices that the bookkeeping of quantum states never promised a film reel of fixed frames. It promised probabilities that are updated consistently when new, compatible information is included. No message runs upstream. The tallies only acquire their shape when you gather them together and look at the whole. You can sketch a human-scale metaphor without losing the thread. Two friends agree to attend different concerts in different towns on the same night. Neither decides in advance which color shirt to wear. A photographer in each town snaps a picture at a randomly chosen moment and records the color. Later, when the albums are compared, a surprising pattern emerges. Whenever the photographers happen to choose the same camera filter, the shirt colors always differ. When different filters were used, the colors match up at a rate that disobeys any guess the friends could have fixed beforehand without communicating. You might be tempted to imagine a hidden text message whispered between towns, but examine each album alone and you see nothing but fair coin tosses, no code, no bias. The pattern lives only in the joint comparison, in the way the albums were sliced, not in a dispatch sent across the miles. Spins and detectors are convenient because they are controllable, but the lesson spills into other corners. Photons with polarization states behave the same way under polarizing filters as electrons do under magnetic measurements. Cold atoms, superconducting qubits, ions in traps, and even defects in crystals have all been coaxed into playing Bell's game. Each time the inequality is tested with care closing, the classic loopholes of detection, efficiency, and locality, the quantum side wins. Over time, the experiments have been woven into devices that certify their own randomness for cryptography, using the very absence of hidden variables as a guarantee that no eavesdropper could have written instruction sheets in advance. The outcome of each trial on each side remains unpredictable. Only the long-run correlations obey the delicate curve that the quantum rules sketch. None of this means that information travels faster than light in any way you could harness. The instant alignment of outcomes across distance does not carry a knob you can turn to make the other side read a chosen word. If you could, you would violate the very structure that keeps space-time consistent, the light cones that define who can influence whom. What you can say is gentler and in its way more beautiful. The universe allows strong, testable relations that cannot be explained by local instruction sheets. Those relations are non-classical and they knit distant events together, but they refuse to become a telegraph. They are like the resonance between strings on a violin. Pluck one and another, tuned just so, will hum in sympathy, not because a note dashed through the wood faster than sound, but because both strings belong to a shared geometry of tension and length. Sit with the result, and a deeper calm arrives. The quantum story is not chaos, it is a different kind of order. Particles do not make things up in a lazy way. They reveal outcomes consistent with a joint state that has been precise all along, just not in the classical sense of pre-filled boxes. Measurements are not magic spells. They are ways of slicing the same object from different angles. Bell handed us a test, a way to ask the world which kind of order it prefers. The world answered with those stubborn 50-50 correlations at certain angles, not the 55% the hidden scripts require. That answer lifts some weight off the puzzle of time. You do not need a courier racing backward along your timeline to explain why correlations appear no matter how late you choose what to ask. You only need to grant that what is, at the quantum level, is not a set of separate facts waiting to be read, but a shared description that becomes particular when touched. Causality survives. The speed limit survives. What changes is the way we picture reality's fabric. Instead of a stack of note cards pinned to each particle, imagine a single score written for two instruments, with harmonies already fixed, even though neither musician has yet seen the page. When the first violin begins, the cello's line is already entangled with it, not because a message jumped the gap, but because the song was always one piece. On nights when this feels too airy, recall that the story has anchors. Laboratories around the world have staged Bell's wager with care that would make a watchmaker smile. Polarizers, switching angles faster than signals can fly between them. Detectors catching the faintest flashes. Random number generators fed by cosmic photons, so no terrestrial conspiracy can choose the settings. Each time, the tally slips the leash of hidden variables and lands on quantum's side. That is not a rumor or a metaphor. It is a stack of data, gently saying that reality at small scales is more tightly woven than our first pictures allowed. And somehow, knowing that, the mind can rest easier, not because the world is simple, but because its strangeness is consistent, measurable, and steady. Like a soft rhythm you can trust, even as it teaches you a new way to count. There's a quieter cousin of the double slit that brings the same mystery into sharper relief. Imagine a simple loop of mirrors and two half-silvered plates, the sort of setup that gently splits and later recombines a single beam. A lone photon enters the first splitter. With equal chance, it is transmitted down one arm or reflected into the other. The two arms meet again, where a second splitter may or may not be waiting. If that second splitter is in place, the two possibilities recombine as waves do. Their phases can add or cancel. Align the lengths just so, and one detector will glow while the other remains dark, as if the photon interfered with itself and chose a single exit by canceling the alternative. Remove the second splitter, and the recombination never happens. Each arm runs to its own detector, and every photon lands at one or the other with no pattern to weave the outcomes together. That contrast already feels like a riddle. Show the photon both paths, and you keep the wave. Demand to know which path, and you get a particle. The delayed choice twist is simple and unnerving. Wait to decide whether the second splitter will be there. Randomly insert it or withdraw it only after the photon has passed the first splitter and is already on its way along one or both arms. Change the rule of the game in the middle of the play. Run this many times. When you later sort the results by what you actually did with the second splitter, the tallies line up with whichever world you created at the last moment. When the splitter was present, you see recombination, one detector bright, the other quiet. just what a wave would produce. When the splitter was absent, you see which path clicks with equal odds, just what particles would yield. The choice made late appears to reach back and decide whether the photon had a path or had both. It's tempting to say the photon somehow knew the future and edited its past. A softer explanation uses nothing but the ordinary quantum rules. A single photon is not a point that must carry a stamped itinerary. It is a quantum state that can be written in different bases. With the second splitter in place, the natural basis is the one that mixes the two arms into bright and dark combinations. The photon is prepared at the first splitter in a superposition of arms. The second splitter asks, are you in the bright combination or the dark? The geometry sets the phases, so only the bright answer is likely. With the splitter removed, the natural basis is simply upper arm or lower arm, and the apparatus asks that question instead. The photon state is projected onto whichever question you end up asking, and the correlations between question and answer look uncanny only if you imagine the answer had to be written before the question existed. In the quantum script, preparation, evolution, and measurement form one sentence. You may choose the last clause late, but the grammar still reads cleanly from start to finish. Two quiet reminders keep causality intact. First, interference is never visible in the click-by-click march of a single detector's record. What you call a pattern only appears when you gather many trials and group them by the setting you actually used. Second, no one at one end can use the late choice to send a message to someone poised at the other end in time to beat a light signal. The statistics seen locally are bland in either case. Only when the full notebook is in hand do the correlations bloom into their delicate shapes. There are other variations that sound even more defiant until you let the air out of the rhetoric. In quantum eraser arrangements, which path information is first marked and then, in a controlled way, erased. When the information remains in principle available, the interference dissolves. When the information is made unknowable in principle, interference returns, but only in properly sorted subsets of the data. In entanglement-assisted versions, the choice to preserve or erase which path information can be made after the photon has already been detected. And yet, when you later pair the records, the conditional fringes appear with crisp loyalty to the choice. No diary is rewritten. No telegram runs upstream. You are discovering which slice of the joint state you created, and the slice you discover determines whether fringes live in that conditional view. If your mind still leans toward retrocausality, you are not alone. Some interpretations invite that language. There are time-symmetric formalisms that treat boundary conditions in both past and future as part of one whole. There are handshake pictures that speak of advanced and retarded waves meeting in agreement. There are retrocausal models that rearrange locality to save an intuitive realism. Others avoid any backward whisper. In many worlds' language, both outcomes exist in separate branches, and the late choice selects the basis in which you describe the branch you occupy. In relational views, outcomes are properties only relative to observers and setups. In pilot wave mechanics, a guiding wave explores both paths, while the particle rides one, and the second splitter alters the guidance at the reunion. The mathematics these stories share is the same, and the no signaling piece remains. Carry the delayed choice story back to the wider theme, and it begins to sound less like a rebellion and more like a reminder. Time, in physics, is a direction in a single fabric with space. A photon does not march from one fixed frame to another like a bead on a wire. It accumulates phase along every path allowed, and the world sums those possibilities. A measurement, whether you place a splitter, whether you keep or erase which path marks, is not a message to the past, but a choice of how to cut through the fabric at the end. The cut you make determines which relations become facts. From a distance, that can resemble a retroactive edit. Up close, it is a consistent stitching of one event to another. There's also kindness in recalling how modest the dramatic words really are when you stand in the lab. The second splitter is not a magical switch that flips history. It is a piece of glass that changes the basis in which the final state is read. The decision to interfere or not is a property of the full apparatus, not a mood swing in a particle. The openness of the quantum state is a resource you shape by design. That is why these same principles power technologies that are pragmatic rather than mystical, interferometers that can hear faint tremors in space-time, clocks that keep time so well that Earth's hills and valleys alter their tick, cryptographic keys whose security rests on the same impossibility of hidden instruction sheets that Bell revealed. The strangeness becomes useful when you accept its terms. And yet, even with the pragmatism, the wonder is allowed to linger. You can still picture a photon approaching a fork and, instead of choosing, learning to be both possibilities at once. You can still feel the hush when a last-moment plate appears and the outcomes reassemble into a quiet stream at one port. You can still imagine the joint state of two far-flung qubits as a chord rather than two notes, a chord that rings true no matter which instrument you decide to hear. None of this asks you to give up the steadiness of cause and effect in your day. It asks only that you grant the world a richer grammar than the one you learned first. We set out with a simple question: why everything you know about time might be wrong, and found instead that some of what you know is right, just incomplete. Time does not tick the same for all. Motion and gravity can stretch or thin it. Light does not merely move. It sets the standard that everything else must keep. Waves are not just spread out smears. They are instructions for how possibilities combine. Particles are not tiny billiard balls. They are events that become definite in context. And the future does not reach back to fix the past. The whole experiment, preparation, paths, choices, detection, writes one self-consistent sentence in a language that is patient with surprise. Hold that sentence gently as the room grows quiet. You do not need to solve the equations to feel their kindness. Somewhere, a clock in a high window is ticking a hair faster than its twin below. Somewhere, a satellite's time is being tuned so your map agrees with your feet. Somewhere, a beam is splitting and rejoining in a dark box, taking both paths and then one, teaching again the lesson that space and time are partners in a dance that never quite looks the same from two corners of the floor. And here, in your own small frame, moments arrive in order, one by one. They carry all this strangeness folded inside, and still they feel simple. That is the quiet gift of the science you've walked through tonight. The universe keeps its promises, even when it keeps them in a larger room than we expected. Close to sleep, it's enough to know the room is there, and that we can visit again whenever curiosity lifts its lantern.